we are going to be talking about negative resistance. Now, the component of the resistor always has a positive value, and this is because fundamentally this component dissipates energy. And if R were to be less than 0, then that means that component would be delivering energy, and that is not something that can happen for a real resistor. However, the equation for resistance is that it's equal to the voltage in divided by the current in. And there's no rule saying this ratio can't be less than 0, just that the physics of a resistor don't allow us to do that. And that's where the negative resistance circuit comes in. And because op amps can deliver power, we're able to build a circuit that can simulate negative resistance. So we are going to begin by analyzing the input resistance between terminal pairs A and B. And let's give this a value of Vn. And I can define a current In, and our input resistance is going to be equal to Vn divided by In. So now let's begin labeling the rest of our component currents. And we have this In value, and that is going to carry around through here because no current goes into my op amp. So this is all going to be In. And we do have a current at the output of our op amp. We can call this I1, and then there's this other current over here, and this is going to be I2. Now the next thing I'm going to do is label my node voltages. Vin is referenced to ground, so I can call this node right here Vin, and that's on the positive input of my op amp, and treating this as an ideal op amp, we're going to have Vin on the negative input as well. And we can call this node right here V1. So at this point, we finished labeling our circuit, and the next thing I'm going to do is write KCL, and we only have one KCL that we need, and that's at V1. And here we have that In plus I1 is equal to I2. And now we can write the equations for our components. And beginning with R1, we have that In is equal to Vn minus V1 divided by R1. Now moving on to this component, I have that I2 is equal to V1 minus Vn divided by R. And I have that I2 is equal to Vn minus 0 divided by R. Now I can equate these two currents together, and I get that V1 minus Vn divided by R is equal to Vn divided by R. And from here, this gives us that V1 equals 2Vn. So we're getting closer to finding the ratio of Vn to In. So now what I need to do is I can take this value for Vn and plug that in right there. And from there, I can find my input resistance. Plugging that in, we have that In is equal to Vn minus 2Vn divided by R1. And rearranging this, we get that Vn divided by In is equal to negative R1. So the input resistance of my op amp is equal to the negative of this component. And this characteristic can be extremely useful. Say I have a capacitor in parallel with an inductor, and these two are connected to a resistor in parallel. Now, if I have energy stored in this circuit, whether in the capacitor's voltage or the inductor's current, and my resistor is sufficiently large, this circuit will oscillate. The output voltage might look something like this, where you have this exponential decay behavior, and that decay is due to energy loss in my resistor and in parasitic resistances in my inductor and in my capacitor. So the interesting thing you can do with negative resistance circuits, say instead that we connect this to the input of my op amp circuit. Now with my capacitor and my inductor connected to my op amp circuit, instead of my voltage across these two components decreasing, it's actually going to be increasing due to the effect of the negative resistance. Due to the limitations of my op amp, the output voltage won't continue to go forever. Eventually, you're going to begin saturating your op amp, where the output value goes to the maximum or minimum value that your op amp can output. But this circuit is one way that you can create an oscillator from an inductor and a capacitor. And that is it for this video on negative resistance. If you enjoyed this video or found it helpful, please like and subscribe. I'll see you next time.